Hi, everyone. My name is Kevin Yarnell. I'm a second semester master's student in mechanical engineering at Duke University. I work in a lab that uses hyperpolarized xenon as contrast for MRIs of the lungs. While working in the lab, I discovered a need for producing the hyperpolarized xenon and decided to make it the focus of my capstone project. So this is a Polarian 9800 hyperpolarizer. It is used to hyperpolarize the xenon gas and dispense it into a dose bag that is given to a subject for a lung MRI scan. This particular polarizer is not very automated, and there are some problems that arise from dispensing the gas. I'll show you a video of the current procedure for producing xenon. Here is a trained technician manually dispensing gas into a dose bag. As you can see, it's quite an involved process requiring all of the technician's attention and quick reflexes to open and close the outflow valves without popping the bag. There's no way for the technician to know the amount of gas in the bag and know if it will rupture. You can see there he just did the plumpness test, which is the official test for measuring the volume. So this procedure did go well, but let me show you what happens when it doesn't. So this is the same technician running through the procedures again, but this time there's a little catch. So one of the valves is not open in time, and the pressure builds up in the polarizer to dangerous levels. You can actually see it jump up to about 65 psi right there. And the polarizer is only rated for about 40 psi. So you can also see that the technician has to react very quickly to prevent damage to the polarizer, rupturing the bag and losing the dose of xenon. This shows there is a need to automate some of the process. I focused on being able to determine the volume in the bag, so that is one less thing for the technician to worry about. The solution I chose to measure how much volume of gas has flowed into the bag was to design a differential pressure flow meter. The flow meter that I created uses Bernoulli's equation and the continuity equation to determine flow rate from pressure. By manipulating them, you can get these two equations, which give you the flow rate. Based off these equations, I designed a prototype to measure the differential pressures. Here's a picture of the prototype and a cross-sectional view of the device. If we look at it a little closer, you can see from the cross-sectional view that one side has a larger diameter than the other, and there are two pressure taps on either side to measure the pressure difference between them. That's the CAD. Let's check it out in real life. I don't have a polarizer with me, so you have to be a little bit imaginative, but this is the polarizer side cap. It has an O-ring in there to prevent any air leaks. So the idea is this would go on the polarizer, and then I would screw this onto my coupling. Then on the dose bag side, we have our dose bag, and we put the cap on to the dose bag, and then the O-ring in between, and then we put the hose and the coupling, screw that on so it's nice and tight. And so the polarizer is going to flow or dispense gas on this side. It's going to go into the dose bag and it will inflate it. Now that I've gone over the device, let's see it in action. Here's a quick video on my device on the polarizer. As you can see, while pumping gas through this device, there is a pressure difference on the manometer. Using this pressure difference, we can find the flow rate with the two equations I spoke of earlier. After finding the flow rate, we can integrate it over time to find the volume of gas in the bag. So that's the basis for my project, trying to find a way to measure the volume of gas that flows into the bag from the polarizer. This prototype has the potential to do just that. If you want to learn more about my project, please visit this website below, and thank you for watching.